Welcome to this lecture on transition metal organometallic chemistry from principles to applications. We have been discussing a very important class of compounds in the last few lectures, and these are transition metal carbonyl complexes. And we in the last lecture we have looked into the reactivity of transition metal carbonyl complexes and as well as their binding mode. Now, with regard to the binding mode of transition metal carbonyl complexes, what we had seen that the binding mode can vary as from being bridging to terminal, and with regard to bridging it can bridge against 2 metal center or 3 metal centers, and depending on how it bridges to metal or how does it bind even in terminal fashion to metal, the new CO stretching frequency is a good marker about the extent of interaction that takes place between the transition metal and the carbonyl moiety. So, what we saw that there are two kinds of interaction. One is CO to transition metal sigma interaction, as well as transition metal to CO pi interaction. This is called sigma donation, and this is called pi back donation. And we had also discussed a particular mode which is not that observed, but this is CO to transition pi donation, which is often neglected, but is observed in sigma bridging kind of binding modes of transition metal carbonyl compounds. Now, of these interaction, what we saw that because of these interaction, the electron density at transition metal varies, electron richness varies, and which affects the mu CO bond. Now, this is the stretching frequency of CO. Now, as the electron richness of the transition metal varies because of this kind of interaction, which can either be donating electron to the transition metal or it can be taking away from the electrons from the transition metal, because of various factors which can be charges, which also can be because of the ligand fragments which is associated with transition metal, how they would affect the transition metal electron richness, and as that electron richness is varies, this nu CO stretching frequencies also varies. And we had taken a couple of examples in this regard, and now with that interplay of this forward sigma, forward pi as well as backward pi donation, we are going to look at a very important part of the reactivity today, which is the trans effect. So, trans effect is the trans ligand, particularly with respect to CO, gets promptly substituted because of the strong binding of CO. Now, trans effect, we are going to try to understand a trans effect by thinking that metal d type orbital interacting with the pi star CO, the way it is drawn over here. Now, usually this is empty, the pi star orbital is empty, and this is d pi filled, and the electron donation happens from metal to the ligand. Now, in a trans effect scenario, we can imagine that there is another competing carbon monoxide ligand which can also suck up this electron density, which is also a pi star empty c orbital can also compete with the central metal atom and suck up the electron density from the metal. So, there may be a competition in the ligand occupying the trans position for this metal filled orbital which contains electrons. So, ligands in trans position compete for electrons of d orbitals of metals. So, electrons in the trans position compete for it. Now, and that is sort of affects or sort of explains the trans effect, or that is where the trans effect arises from. Now, one can imagine that this trans ligand, instead of being a CO, it can be another ligand which can compete for the electron density of the metal bound trans to the carbonyl moiety, and this is explained through this diagram. CO So, in this case this is a d pi field and this is a pi star empty, and the electron donation happens in this direction. Now, imagine a ligand with an empty orbital of appropriate pi symmetry which is empty and would also like to compete for this electron of the d orbital of the central metal atom. As a result, these, because of the competition, one ligand would try to weaken the trans ligand in terms of bond strength, because it would do so by sucking away all the electron density onto itself. As a result, back donation would not happen at the trans ligand and thereby it becomes weakened. So, replacing carbon monoxide by a ligand which is a weak pi acceptor, this trans metal CO bond is strengthened. So, if a CO is replaced by a weak pi acceptor, then the CO itself will suck away most of the electron density from the metal to itself. As a result, the metal CO bond will be strengthened and that would be reflecting in lowering of the CO stretching frequency. Now, this is very nice illustrated in this series of examples where we saw that replacing carbon monoxide by weak pi ligands lead to decreasing in the new CO stretching frequency. So, here are example of some complexes showing this trans effect of CO. For example, in P F3 MO CO3 3, new CO centimeter inverse is 2055, 2090. That means that PF3 fluorine being highly electronegative atom is sucking away some electron density from molybdenum on towards itself. As a result, CO cannot engage in too much of back bonding from molybdenum d orbital. As a result, the CO stretch in this complex is quite high. Now, if one goes from PF3 to PCl3, now fluorine has been replaced by less electronegative Cl. That means the molybdenum center would be more electron rich, and hence the molybdenum would back donate more to carbon monoxide. As a result, CO stretch would decrease, and indeed it decreases significantly to 1991 and 2040. Now, this 1991 is the CO which are trans, and these are the two modes depending on the combinations of the COs. Now, if one goes from PCl3 to POMe3, whole 3 MoCO3, which is more electron rich, and sort of it goes to 1888, 1977. Some more examples like PPH3, MoCO3, 1835, 1934, CH3CN, where nitrogen is coordinated of acetonitrile moiety onto molybdenum, CO3, even further 1783, 1915, di-En, molybdenum, CO3, 1758, 1898 to PY3, pyridine, molybdenum, CO3, 1746 to 1888. So, what we see that on going down, as the electron density of molybdenum increases, richness increases, that leads to enhanced molybdenum to CO pi back donation. As a result, CO stretching frequency decreases. So, this gives us a quantitative or semi quantitative feel for the extent of pi back donation that may arise by substitution of a pi acidic ligand CO by more electron donating ligands, and that will be reflected in the new CO stretching frequency as is shown over here. Now, let us move to the reactivity of transition metal carbonyl complexes, and the primarily these are mainly of substitution reaction, where CO undergoes a substitution reaction. Now, COs can be replaced by thermally or photochemically, replaced by thermal or photochemical method means. For example, Cr CO6 when heated in acetonitrile, eliminates 3 molecules of CO, 2 gives CH3CN whole 3 Cr CO3, and when that is treated with another olefin, cyclic olefin C7H8, it eliminates 3 molecules of CH3CN to give CrCO3. Now, the way the substitution happened is that CO is first replaced by a Labar ligand, followed by the addition of the second ligand. Now, this is a standard method for synthesizing low oxygen state carbonyl complexes. Now, this was done thermally. The same strategy can be used photochemically. For example, reaction of this with C8H14 in H nu eliminates CO to give this CrCO5, and then this labile ligand is replaced by the ligand for which the substitution reaction is being tried to give CrCO5L. So, this method of photochemically as well as thermally substituting CO initially by replacing it by a labile ligand followed by other ligand, this is a standard method for synthesizing low oxidation state complexes and this is done by initial introduction of a labile ligand followed by various other ligands. Now, these complexes where COs have been partially replaced by a labile ligand, these are called metal-carbonyl-transfer agents, because they can be used for synthesizing low oxidation state carbonyl heteroleptic complexes. So, these are called metal-carbonyl-transfer agents. The examples include THF, molybdenum pentacarbonyl, CH2Cl2 chromium pentacarbonyl, and cyclooctane whole 2 Fe tricarbonyl. So, these are designated as methyl transfer agent. Usually, these carbonyl substitution reaction occur at 18 electron valence complexes and follows dissociative pathway. This is illustrated by the following examples shown below. Carbonyl substitution reaction at 18 VE complex, CrCO6, slow, because this is already a 18 VE complex, and what it means that this is quite stable. So, no wonder it is slow to dissociate a carbon monoxide to give chromium pentacarbonyl, which is a 16 valence electron complex, and this is very fast in reacting with the ligand of choice to give CrCO5L. Now, this reaction is governed by dissociation energy of chromium carbonyl, and DCrCO bond of chromium carbonyl bond is about 155 kilojoules per mole. Whereas, if one were to look at the same reaction for nickel tetracarbonyl, NiCO4, which also is a 18 valence electron complex, it eliminates CO to give nickel tricarbonyl, which is a 16 valence electron complex, and that reacts with L to give nickel tricarbonyl L. Now, with regard to nickel carbonyl bond dissociation energy, nickel carbonyl bond is much weaker than the above mentioned chromium carbonyl bond, and this bond energy is about 105 kilojoule per mole. And the reason that nickel reacts faster is because this has much weaker this nickel carbonyl bond, and as a result that nickel CO4 reacts faster than CrCO6, because the bond dissociation energy of nickel carbonyl is much weaker than that of chromium carbonyl. Now, one thing which is evident by comparing the reactivity for these two pairs of reaction is the fact that delta H enthalpy change of these reactions are identical to or depends on the bond energy of the MCO bond. So, as we saw that nickel carbonyl bond was much weaker than the chromium carbonyl, hence the reactivity of nickel tetracarbonyl was much higher, or nickel tetracarbonyl substitution occurred much faster than that of the chromium tetracarbonyl. This rate of substitution, which was found that is highest for the central element, was highest for the second row element, transition metal, though the reason is not clearly understood. For example, for chromium, molybdenum, tungsten, molybdenum showed higher reactivity than chromium and tungsten. For cobalt, rhodium, iridium, rhodium showed higher reactivity for cobalt and iridium, and for palladium, nickel and platinum, palladium showed higher reactivity over nickel. So, this substitution reaction also for 17 electron species is slightly different, because for the 18 electron species what we had seen that it underwent substitution in a dissociative fashion, whereas the 17 electron species the substitution reaction is formed by associative mechanism. So, 17 VE complex undergo substitution reaction via associative mechanism, and this is shown by the example given. So, VCO6, this is the 17 valence electron species. It is slow to add this electron, which is VCO6L. Now, it has become a 19 valence electron species, which is highly unstable. As a result, it rapidly eliminates carbon monoxide to give VCO5L, which again is a 17 valence electron species. Now, it is interesting to note that 17 VE valence electron vanadium carbonyl species reacts 10 to the power 10 times faster than the 18 VE CO6, which is 18 valence electron species. So, this is an interesting observation which shows that unlike the 18 VE species which undergoes dissociative mechanism, 17 VE species undergoes associative mechanism, and that 17 VE species reacts 10 to the power 10 times faster than the 18 valence electron species. So, with that I would like to conclude today's lecture, and would like to summarize the points that we have developed today, particularly with respect to the reactivity of transition metal carbonyl complexes. And to begin with, we have started looking at several transition metal carbonyl complexes, and we had seen how the variation of the electron density at the metal affected the new CO stretching frequencies, and this we have looked at particularly with respect to the trans effect, where the ligand trans to the carbonyl ligand competes with the electron density of the central metal atom, and because of its weak pi accepting nature leads to strong metal carbonyl bond, and thereby weakening the metal trans other ligand bond, and which can readily be substituted. Now, the effect of the trans effect was observed in substitution reactions, where 18 valence electron complexes under photochemical conditions or like thermal conditions eliminated carbon monoxides, and then were replaced in turn by labile ligands, which then were substituted by other ligands. So, these in this set a series of heteroleptic labile ligand metal carbonyl complexes were designed, and these are known as carbonyl transfer agents. We have also looked at the mechanism of substitution that occur for metal carbonyl complexes, and what we had seen that there is a distinct mechanistic pathway that is observed for the 18 electron species as well as that of the 17 electron species. It was noted that 18 electron species undergo dissociative pathway, whereas 17 electron species undergo associative pathway, and lastly it was shown that for vanadium hexacarbonyl complexes the 17 electron species was found to undergo substitution reaction at a tremendously rapid pace of about 10 to the power 10 times faster than the corresponding 18 electron chromium hexacarbonyl complex. So, with this I would like to conclude this lecture on the reactivity of transition metal carbonyl complexes for today, and we are going to discuss and take up some more of the reactions of transition metal carbonyl complexes in the next lecture. Until that, I thank you for being with me in this lecture and look forward to being with you in the next lecture, where we are going to look up at the reactivity of transition metal carbonyl complexes in with more details. Till then, goodbye and thank you.